So in the upsample box, are you deconvolution? I mean, what are you doing there? You're just copying the values, or you're applying a deconvolution?
I think in this paper, this was not a fractionally strided convolution. I think it was instead some kind of a fixed upsampling, like a bilinear interpolation or something like that. Or maybe even a nearest neighbor, just something fixed, not learnable. But I could be wrong. But you could definitely imagine swapping in some learnable thing there, too. OK, so this actually is very similar to RCNN. But in the detection lecture, we saw that RCNN was just the start of the story. There's all these faster versions, right? So it turns out that a similar intuition from faster RCNN has actually been applied to this instance segmentation problem as well. So this is work from Microsoft that and this model actually won the COCO instance segmentation challenge this year. So they took their giant ResNet and they stuck this model on top of it, and they crushed everyone else in the COCO instance segmentation challenge. So this actually is very similar to faster RCNN. So we're going to take our input image, and just like in fast and faster RCNN, our input image will now be pretty high resolution, and we'll get this giant convolutional feature map over our high resolution image. Then from this high-resolution image, we're actually going to propose our own region proposals. In the previous method, we relied on these external segment proposals. But here, we're just going to learn our own region proposals, just like faster RCNN. So here, we just stick a couple extra convolutional layers on top of our convolutional feature map. And each one of those is going to predict several regions of interest in the image that using this idea of anchor boxes that we saw in the detection work. The difference is that now, once we have these region proposals, we're going to segment them out using a very similar approach that we just saw on the last slide. So for each of these proposed regions, we're going to use this ROI, what do they call it, ROI warping or pooling, and squish them all down to a fixed square size, and then run each of them through a convolutional neural network to produce these coarse figure ground segmentation masks, like we just saw in the previous slide. So now at this point, we've gotten our image, we've gotten a bunch of region proposals, and now for each region proposal, we have a rough idea of which part of that box is foreground and which part is background. Now we're going to take this idea of masking. So now that we've predicted the foreground background for each of these segments, we're going to mask out the predicted background and only keep the pixels from the predicted foreground, and pass those through another couple layers to actually classify that segment as our different object categories. So this is, and then this entire thing can just be learned jointly end to end, with the idea that we've sort of got these three semantically interpretable outputs in intermediate layers of our network, and each of them we can just supervise with ground truth data. So for these regions of interest, we know where the ground truth objects are in the image, so we can provide supervision on those outputs. For these segmentation masks, we know what the true foreground and background are, so we can give supervision there. And we obviously know the classes of those different segments. So we just provide supervision at different layers of these network and try to trade off all of those different loss terms and hopefully get the thing to converge. But this actually was trained end to end, and they fine-tuned into ResNet, and it works really, really well. So here is the results figure that we have to show. So these results are, at least to me, really, really impressive. So for example, this input image has all these different people sitting in this room. And the predicted outputs do a really good job of separating out all those different people, even though they overlap, and there's a lot of them, and they're very close. Same with these cars. Maybe that one's a little easier, but especially this people one I was pretty impressed by. But you can see it's not perfect. So this potted plant it thought was blobbier than it really was, and it confused this chair on the right for a person, and it missed a person there. But overall, these results are very, very impressive. And like I said, this model won the COCO segmentation challenge this year. So the overview of segmentation is that we've got these two different tasks, semantic segmentation and instance segmentation. For semantic segmentation, it's very common to use this conv-deconv approach. And then for instance segmentation, you end up with these pipelines that look more similar to object detection. So if there's any last-minute questions about segmentation, I can try to answer those now. Nope, super clear, I guess. So we're going to move on to another pretty cool, exciting topic, and that's attention models. So this is something that I think has gotten a lot of attention in the last year in the community. As a kind of a case study, we're going to talk about the model from, I don't have the citation here. Okay, but as a sort of a case study, we're going to talk about the idea of attention as applied to image captioning. So I think this model was previewed in the recurrent networks lecture, but I want to step into a lot more detail here. But first, as a recap, just so we're on the same page, hopefully you know how image captioning works by now, since the homework is due in a few hours. But we're going to take our input image and run it through a convolutional net and get some features. Those features will be used maybe to initialize the first hidden state of our recurrent network. Then our start token, or our first word, together with that hidden state, we're going to produce this distribution over words in our vocabulary. Then to generate a word, we'll just sample from that distribution. And we'll just sort of repeat this process over time to generate captions. The problem here is that this network only sort of gets one chance to look at the input image. And when it does, it's looking at the entire input image all at once. And it might be cooler if it actually had the ability to, one, look at the input image multiple times, and also if it could focus on different parts of the input image as it ran. So a pretty cool paper that came out last year was this one called Show, Attend, and Tell. The original was Show and Tell, so they added the attend part. And the idea is pretty straightforward. So we're going to take our input image, and we're still going to run it through a convolutional network. But instead of extracting the features from the last fully connected layer, instead we're going to pull features from one of the earlier convolutional layers. And that's going to give us this grid of features rather than a single feature vector. So because these are coming from convolutional layers, you can imagine that maybe the upper left-hand, you can think of this as a 2D spatial grid of features. And inside each grid, each point in the grid gives you features corresponding to some part of the input image. So now, again, we'll use these features to initialize the hidden state of our network in some way. And now here's where things get different. Now we're going to use our hidden state to compute not a distribution over words, but instead a distribution over these different positions in our convolutional feature map. So again, this would probably be implemented with maybe an affine layer or two, and then some softmax to give you a distribution. But we just end up with this L-dimensional vector giving us a probability distribution over these different locations in our input. And now we take this probability distribution and actually use it to give a weighted sum of those feature vectors at the different points in our grid. So once we take this weighted combination of features, that takes our grid and summarizes it down to a single vector. This sort of z vector summarizes the input image in some way. And due to the different types, due to this probability distribution, it gives the network the capacity to focus on different parts of the image as it goes. So now this weighted vector that's produced from the input features gets fed together with the first word. And now when we make our recurrence in our recurrent network, we actually have three inputs. We have our previous hidden state, we have this attended feature vector, and we have this first word. And now all of these together are used to produce our new hidden state. And now from this hidden state, we're actually going to produce two outputs. We're going to produce a new distribution over the locations in our input image, and we're also going to produce our standard distribution over words. So these would probably be implemented as just a couple of fully connected layers on top of the hidden state. And now this process repeats. So given this new probability distribution, we go back to the input feature grid and compute a new summarization vector for the image. Take that vector together with the next word in the sentence to compute the new hidden state. Produce. Okay, so that spoiled it a little bit. But but then we'll actually repeat this process over time to generate our captions. Yeah, question.
Can you explain one more time how the features, the LBT features array is generated? So that's when you take a given convolutional layer of your network, and then you just take the output of one filter. And that's what you do.
So the question is where does this feature grid come from? And the answer is when you're doing an AlexNet, for example, you have conv1, conv2, conv3, conv4, conv5. And by the time you get to conv5, the shape of that tensor is now something like 7 by 7 by 512. So that corresponds to a 7 by 7 spatial grid over the input. And in each grid position, that's a 512 dimensional feature vector. So those are just pulled out of one of the convolutional layers in the network. Yeah, question?
So the probability distribution is for the distribution of classes or like the distribution of words over the allocation or what?
So the question is about these probability distributions. So we're actually producing two different probability distributions at every time step. The first one are these D vectors in blue. So those are a probability distribution over words in your vocabulary, like we did in normal image captioning. And also at every time step, we'll produce a second probability distribution over these locations in the input image that are telling us where we want to look on the next time step. So this is actually quite right. So you're just doing two outputs. And then as a quiz, I wanted to see like what framework you wanted to use to implement this. And we talked about maybe how RNNs would be a good choice for Theano or TensorFlow. And I think this qualifies as a crazy RNN. So I wanted to maybe talk in a little bit more detail how these summarization vectors get produced. So this paper actually talks about two different methods for generating these vectors. So the idea, as we saw on the last slide, is that we'll take our input image and get this grid of features coming from one of the convolutional layers in our network. And then for each time step, our network will produce this probability distribution over locations. So this would be a fully connected layer and then a softmax to normalize it. And now the idea is that we want to take these, this grid of feature vectors together with these probability distributions and produce a single d-dimensional vector that summarizes that input image. And the paper actually explores two different ways of solving this problem. So the easy way is to use what they call soft attention. So here, our d-dimensional vector z will just be a weighted sum of all the elements in the grid, where each vector is just weighted by its predicted probability. This is actually very easy to implement. It's sort of a nice, it's just another layer in a neural network. And these gradients, like the derivative of this context vector with respect to our predicted probabilities p, is quite nice and easy to compute. So we can actually train this thing just using normal gradient descent and backpropagation. But they actually explore another option for computing this feature vector, and that's something called hard attention. So instead of having this weighted sum, we might want to select just a single element of that grid to attend to. So you might imagine, so one simple thing to do is just to pick the element of the grid with the highest probability and just pull out the feature vector corresponding to that argmax position. The problem is now if you think about in this argmax case, if you think about this derivative, the derivative of z with respect to our distribution p, it turns out that this is not very friendly for backpropagation anymore. So imagine in an argmax case, suppose that PA were actually the largest element in our input. And now what happens if we change PA just a little bit? So if PA is the argmax and then we just jiggle the probability distribution just a little bit, then PA will still be the argmax. So we'll still select the same vector from the input, which means that actually the derivative of this vector z with respect to our predicted probabilities is going to be 0 almost everywhere. So that's very bad. Now we can't really use backpropagation anymore to train this thing. So it turns out that they propose another method based on reinforcement learning to actually train the model in this context where you want to select a single element of the input. But that's a little bit more complex, so we're not going to talk about that in this lecture. But just be aware that that is something that you'll see, this difference between soft attention and hard attention, where you actually pick one. So now we can look at some pretty results from this model. So since we're actually generating a probability distribution over grid locations at every time step, we can visualize that probability distribution as we generate each word of our generated caption. So then for this input image that shows a bird, both their hard attention model and their soft attention model in this case both produce the caption, a bird flying over a body of water, period. And for these two models, they've visualized what that probability distribution looks like for these two different models. So the top shows the soft attention, so you can see that it's sort of diffuse since it's averaging probabilities from every location in the image. And in the bottom, it's just showing the one single element that it pulled out. And these actually have quite nice semantic interpretable meanings. So you can see that when the model is, especially the soft attention on the top, I think gives very nice results. That when it's talking about the bird and talking about flying, it sort of focuses right on the bird. And then when it's talking about the water, it kind of focuses on everything else. So another thing to point out is that it didn't receive any supervision at training time for which parts of the image it should be attending to. It just made up its own mind to attend to those parts based on whatever would help it caption things better. And it's pretty cool that we actually get these interpretable results just out of this captioning task. We can look at a couple other results because they're fun. So we can see that when we have the dog throwing a woman throwing a frisbee in the park, it focuses on the frisbee. Talking about the dog, it learns to recognize the dog. And especially interesting is this guy in the bottom right. When it generates the word trees, it's actually focusing on all the stuff in the background and not just the giraffe. And again, these are just coming out with no supervision, all just based on the captioning task. Question?
Can you, I don't know if you talked about this, but when hard attention you prefer over soft attention?
Yeah, so the question is, when would you prefer hard versus soft attention? So there's, I think, sort of two motivations that people usually give for wanting to even do attention at all in the first place. One of those is just to give nice interpretable outputs, and I think you get nice interpretable outputs in either case, at least theoretically. Maybe their hard attention figure wasn't quite as pretty. But the other motivation for using attention is to relieve computational burden. Especially when you have a very, very large input, it might be computationally expensive to actually process that whole input on every time step. And it might be more efficient computationally if we can just focus on one part of the input at each time step and only process a small subset per time step. So with soft attention, because we're doing this sort of averaging over all positions, we don't get any computational savings. We're still processing the whole input on every time step. But with hard attention, we actually do get a computational savings, since we're explicitly picking out some small subset of the input. So I think that's the big benefit. Also, hard attention takes reinforcement learning, and that's fancier and makes you look smarter. So that's kind of cool. Question?
Can you give some intuition for how the network is learning these when it never knows, like there's no technical, it doesn't know which pixels are a frisbee or whatever?
Yeah, so the question is, how does this work at all? And I think the answer is it's really learning sort of correlation structures in the input, right? That it's seen many examples of images with dogs, and it's seen many sentences with dogs. But for those different images with dogs, the dogs tend to appear in different positions in the input. And I guess it turns out through the optimization procedure that actually putting more weight on the places where the dog actually exists actually helps the captioning task in some way. So I don't think there's a very good answer. It just happens to work. Also, I'm not so obviously these are pictures from a figure, or these are figures from a paper, not like random results. So I'm not sure how good it works on random images. But another thing to really point out about this, especially this model of soft attention, is that it's sort of constrained to this fixed grid from the convolutional feature map. That these, like we're getting these nice diffuse looking things, but those are just sort of like blurring out this, this distribution. And the model does not really have the capacity to look at arbitrary regions of the input. It's only allowed to look at these fixed grid regions. I should also point out that this idea of soft attention was not really introduced in this paper. I think the first paper that really had this notion of soft attention came from machine translation. So here it's a similar motivation, that we want to take some input sentence here in Spanish and then produce an output sentence in English. And this would be done with a recurrent neural network sequence-to-sequence model, where we would first read in our input sentence with a recurrent network, and then generate an output sequence very similar as we would in captioning. But in this paper, they wanted to actually have attention over the input sentence as they generated their output sentence. So the exact mechanism is a little bit different, but the intuition is the same. That now, when we generate this first word my, we want to compute a probability distribution not over regions in an image, but instead over words in the input sentence. So here, we're going to get a distribution that hopefully will focus on this first word in the Spanish sentence, and then we'll take some features from each word and then reweight them and feed them back into the RNN at the next time step. And this process would repeat at every time step of the network. So this idea of soft attention is very easily applicable not only to image captioning, but also to machine translation. Question?
How do you do it for variable length sentences?
The question is, how do you do this for variable length sentences? And that's something I glossed over a little bit. But the idea is you use what's called content-based addressing. So for the image captioning, we know ahead of time that there's this fixed maybe 7x7 grid. So we just produce a probability distribution directly. Instead, in this model, as the encoder reads the input sentence, it's producing some vector that encodes each word in the input sentence. So now in the decoder, instead of directly producing a probability vector, a probability distribution, it's going to spit out sort of a vector that will get dot producted with each of those encoded vectors in the input. And then those dot products get used to get renormalized and converted to a distribution. So this idea of soft attention is actually pretty easy to implement and pretty easy to train. So it's been very popular in the last year or so, and there's a whole bunch of papers that apply this idea of soft attention to a whole bunch of different problems. So there have been a couple papers looking at soft attention for machine translation, as we saw. There have been a couple papers that actually want to do speech transcription, where they read in an audio signal and then output the words in English. So there have been a couple papers that use soft attention over the input audio sequence to help with that task. There's been at least one paper on using soft attention for video captioning. So here you read in some sequence of frames, and then you output some sequence of words. And you want to have attention over the frames of the input sequence as you're generating your caption. So you could see that maybe for this little video sequence, they output someone is frying a fish in a pot. And when they generate the word someone, they actually attend much more to this second frame in the video sequence. And when they generate the word frying, it attends much more to this last element in the video sequence. There have also been a couple papers for this task of question answering. So here, the setup is that you read in a natural language question, and you also read in an image, and the model needs to produce an answer about that question, produce the answer to that question in natural language. And there have been a couple papers that explore the idea of spatial attention over the image in order to help with this problem of question answering. Another thing to point out is that some of these papers have great names. So there was show and tell, there was show attend and tell, there was listen, attend, and spell, and this one is ask, attend, and answer. So I really enjoy the creativity with naming on this line of work. And this idea of soft attention is pretty easy to implement, so a lot of people have just applied it to tons of tasks. But remember, we saw this problem with this sort of implementation of soft attention, and that's that we cannot attend to arbitrary regions in the input. Instead, we're constrained and can only attend to this fixed grid given by the convolutional feature map. So the question is whether we can overcome this restriction and still attend to arbitrary input regions somehow in a differentiable way. And I think a precursor to this type of work is this paper from Alex Graves back in 2013. So here he wanted to read as input a natural language sentence and then generate as output actually an image that would be handwriting, like writing out that sentence in handwriting. And the way that and this actually has attention over this output image in kind of a cool way, where now he's actually predicting the parameters of some Gaussian mixture model over the output image, and then uses that to actually attend to arbitrary parts of the output image. And this actually works really, really well. So on the right, some of these are actually written by people, and the rest of them were written by his network. So can you tell the difference between the generated and the real handwriting? I couldn't. So it turns out that the top one is real, and these bottom four are all generated by the network.
And you can see the P is kind of a unique P in the real one.
Yeah, so then maybe the real ones have more variance between the letters or something like that. But these results work really well. And actually, he has an online demo that you can go on and try that runs in your browser. You can just type in words, and it'll generate the handwriting for you. So that's kind of fun. Another paper that we saw already is Draw, that sort of takes this idea of arbitrary attention over and then extends it to a couple more real-world problems, not just handwriting generation. So one task they consider is image classification. Here we want to classify these digits, but in the process of classifying, we're actually going to attend to arbitrary regions of the input image in order to help with this classification task. So this is kind of cool. It sort of learns on its own that it needs to attend to these digits in order to help with image classification. And with draw, they also consider the idea of generating arbitrary output images with a similar sort of motivation as the handwriting generation, where we're going to have arbitrary attention over the output image and just generate this output bit by bit. And I think we saw this video before, but it's really cool. So this is the draw network from DeepMind. So you can see that here we're doing a classification task. So it sort of learns to attend to arbitrary regions in the input. And when we generate, we're going to attend to arbitrary regions in the output to actually generate these digits. So it can generate multiple digits at a time, and it can actually generate these house numbers. So this is really cool. And as you could see, like the region it was attending to was actually growing and shrinking over time and sort of moving continuously over the image. And it was definitely not constrained to a fixed grid like we saw with show, attend, and tell. So the way that this paper works is a little bit weird. And some follow-up work from DeepMind, I think, actually was more clear. And why is this guy? Oh, my focus is all off. OK. Right, so there's this follow-up paper that uses a very similar mechanism for arbitrary attention called spatial transformer networks, but I think is much easier to understand and presented in a very clean way. So the idea is that we want to have this input image, our favorite bird, and then we want to have this sort of continuous set of variables telling us where we want to attend. So you might imagine that we have the center and width and height of some box of the region we want to attend to. And then we want to have some function that takes our input image and these continuous attention coordinates and then produces some fixed size output. And we want to be able to do this in a differentiable way. So this seems kind of hard, right? Because you imagine that, at least with the idea of cropping, then these inputs cannot really be continuous. They need to be sort of pixel values, so we're constrained to integers. And it's not really clear exactly how we can make this function continuous or differentiable. And they actually came up with a very nice solution. And the idea is that we're going to write down a parameterized function that will map from coordinates of pixels in the output to coordinates of pixels in the input. So here, we're going to say that this upper right-hand pixel in the output image has the coordinates xt, yt in the output. And we're going to compute these coordinates xs and ys in the input image using this parameterized affine function. So that's a nice differentiable function that we can differentiate with respect to these affine transform coordinates. Then we can repeat this process, and again, for maybe the upper left-hand pixel in the output image, we again use this parameterized function to map to the coordinates of the pixel in the input. Now we can repeat this for all pixels in our output, which gives us something called a sampling grid. So the idea is that this would be our output image, and then for each pixel in the output, the sampling grid tells us where in the input that pixel should come from. And now, have any of you guys taken a computer graphics course? Not many? So this looks kind of like texture mapping, doesn't it? So they take this idea from texture mapping in computer graphics and just use bilinear interpolation to compute the output once we have this sampling grid. So now this allows our network to actually attend to arbitrary parts of the input in a nice differentiable way, where our network will now just predict these transform coordinates theta, and that will allow the whole thing to attend to arbitrary regions of the input image. So they put this thing all together into a nice little self-contained module that they call a spatial transformer. So the spatial transformer receives some input, which you can think of as our raw input image, and then actually runs this small localization network, which could be a small fully connected network or a very shallow convolutional network. And this localization network will actually produce as output these affine transform coordinates theta. Now these affine transform coordinates will be used to compute a sampling grid. So now that we've predicted this affine transform from the localization network, we map each pixel in the output, the coordinates of each pixel in the output, back to the input. And this is a nice, smooth, differentiable function. Now, once we have the sampling grid, we can just apply bilinear interpolation to compute the values in the pixels of the output. If you think about what this thing is doing, it's clear that every single part of this network is 1, continuous, and 2, differentiable. So this thing can be learned jointly without any crazy reinforcement learning stuff, which is quite nice. Although one sort of caveat to note about bilinear sampling, if you know how bilinear sampling works, it means that every pixel in the output is going to be a weighted average of 4 pixels in the input. So those gradients are actually very local. So this is continuous and differentiable and nice, but I don't think you get a whole lot of gradient signal through the bilinear sampling. But once you have this nice spatial transformer module, we can just insert it into existing networks to sort of let them learn to attend to things. So they consider this classification task very similar to the draw paper, where they want to classify these warped versions of MNIST digits. So they actually consider several other more complicated transforms, not just these affine transforms. You could also imagine that, so that's the mapping from your output pixels back to your input pixels. On the previous slide, we showed an affine transform, but they also consider projective transforms and also thin plate splines. But the idea is you just want some parametrized and differentiable function, and you could go crazy with that part. So here on the left, the network is just trying to classify these digits that are warped. So on the left, we have different versions of warped digits. On this middle column is showing these different thin plate splines that it's using to attend to a part of the image. And then on the right, it shows the output of the spatial transformer module, which has not only attended to that region, but also unwarped it, corresponding to those splines. And on the right, they're using an affine transform. On the right is using an affine transform, not these thin plate splines. So you can see that this is actually doing more than just attending to the input. We're actually transforming the input as well. So for example, in this middle column, this is a 4, but it's actually rotated by something like 90 degrees. So by using this affine transform, the network can not only attend to the 4, but also rotate it into the proper position for the downstream classification network. And this is all very cool. And again, sort of similar to the soft attention, we don't need explicit supervision. It can just decide for itself where it wants to attend in order to solve the problem. So these guys have a fancy video as well, which is very impressive. So this is the transformer module that we just unpacked. And here we're actually showing, right, so this is actually running a classification task, but we're varying the input continuously. So you can see that for these different inputs, the network learns to attend to the digit, and then actually canonicalizes that digit to sort of a fixed known pose. And as we vary that input and move it around the image, the network still does a good job of locking on to the digit. And on the right, you can see that sometimes it can fix rotations as well. Right? So here on the left, we're actually rotating that digit, and the network actually learns to unrotate the digit and canonicalize the pose. And again, both with affine transforms or thin plate splines. So this is using even crazier warping with projective transforms. So you can see that it does a really good job of learning to attend and also to unwarp. And they do quite a lot of other experiments. Instead of classification, they learn to add together 2 warped digits, which is kind of a weird task, but it works. So the network is receiving 2 inputs as 2 input images, and it needs to output the sum. And it learns, and even though this is kind of a weird task, it learns that it needs to attend and unwarp those images. So this is during optimization. Right, so this is a task called co-localization. So the idea is that the network is going to receive 2 images as input that are maybe 2 different images of 4s, and the task is to say whether or not those images are the same or different. And then also using spatial transformers, it ends up learning to localize those things as well. So you can see that over the course of training, it learns to actually localize these things very, very precisely. Even when we add clutter to the image, then these networks still learn to localize very, very precisely. So that's a recent paper from DeepMind that is pretty cool. So any other last-minute questions about spatial transformers? Yeah.
So just to clarify, so what exactly is the y variable in this concept? The y variable is just like digitize?
Yeah. So the question is what is the task that these things are doing? And at least in the vanilla version, it's just classification. So it receives this sort of input digit, which could be warped or cluttered or whatnot, and all it needs to do is classify the digit. And sort of in the process of learning to classify, it also learns to attend to the correct part. So that's a really cool feature of this work. All right, so then the sort of my overview of attention is that we have soft attention, which is really easy to implement, especially in this context of fixed input positions, that we just produce distributions over our input and then reweight and refeed those vectors back to the network somehow. And this is really easy to implement in many different contexts and has been implemented for a lot of different tasks. When you want to attend to arbitrary regions, then you need to get a little bit fancier. And I think spatial transformers is a very nice, elegant way of attending to arbitrary regions in input images. There are a lot of papers that actually work on hard attention, and this is quite a bit more challenging due to this problem with the gradients. So hard attention papers typically use reinforcement learning, and we didn't really talk about that today. So any other questions about attention or, okay, sure.
So a quick question about your presentation. So before you introduced the concept of spatial transformer networks, you gave us some examples of captured images using sort of the fixed input locations.
Yeah.
Were those results produced using only the grid-based?
Yeah, so the question is about the captioning before we got to spatial transformers. And yeah, those captions were produced using this grid-based thing. But in that network in particular, I think it was a 14 by 14 grid. So it has quite a lot of locations, but it still is constrained to where it's allowed to look. Question?
So is there any interpretation between soft attention and hard attention?
The question is about interpolating between soft attention and hard attention. So yeah, one thing you might imagine is you train the network in a soft way, and then during training you kind of penalize it to make that distribution sharper and sharper and sharper, and then at test time you just switch over and use hard attention instead. And I think I can't remember which paper did that, but I'm pretty sure I've seen that idea somewhere. But in practice, I think training with hard attention tends to work better than this sharpening approach. But it's definitely something you could try. Okay, if no other questions, then I think we're done a couple minutes early today. So get your homework done.